is titled as Spectroscopy. So if you want to open your exercise books at this point and put down the title as Spectroscopy, titled as Spectroscopy. So if you want to open your exercise books at this point and put down the title as Spectroscopy, this is an internal standard, so I don't know if you want to change your exercise book. You can have a different book for this standard. The achievement standard number is 91388 and is also you can find resources under Chem 3.2. So those are the two numbers that you can use to find more resources online. It is worth 3 credits and it's assessed in school. So really what they're looking for is they want you to, I'll read what the achievement objective is. They want you to investigate and measure the chemical and physical properties of a range of group of substances. So they want you to measure chemical and physical properties of a range of substances. They want you to apply knowledge of chemistry to explain aspects of the natural world and how chemistry is used in society to meet needs, resolve issues, and develop new technologies. So I'll probably go and show you some of the new methods of how spectroscopy is changing the way the food industry and other industries are being changed because of this technique, analytical technique called spectroscopy, but we'll do that when I'm in class. For today, I'm just going to stick to a basic introduction. Now, you can read all of this a little bit later. We've got this continuing chemistry book at home. That's where I've taken that from. But it'll probably not make a lot of sense now, so I'm just going to get into the introduction. So there we go. Spectroscopy is what we are going to be looking at over the next 2 to 3 weeks. What is spectroscopy? Okay, spectroscopy is the study of the way electromagnetic radiation, which is light, interacts with matter. So you pass light through matter, and matter interacts a certain way with a certain wavelength. So that's basically what it is the study of the way electromagnetic radiation interacts with matter. You can pause the video at this point and copy that definition. Just title it as "What is spectroscopy?" and then copy the definition. Now the next new terminology you're going to see here is called the word spectrometer. What is a spectrometer? A spectrometer is an instrument that is used for viewing the results of this interaction between electromagnetic radiation and a sample. Alright, so you can copy this as well. What is a spectrometer? A spectrometer is an instrument, so it's a tool that a chemist uses to view the results of the interaction between electromagnetic radiation and any sample or chemical that we want to analyze. Alright, so you can pause the video and again copy this down as a definition for what is a spectrometer. Now we've been talking a lot about this word electromagnetic radiation, and although the assessment doesn't really go into it, just some background info for you. What is electromagnetic radiation? Electromagnetic radiation is a form of energy. It shows wave-like behavior as it passes through space. You don't have to copy this, and some of you who take physics may know a little bit more than this, but I'm trying to keep it as basic as possible. What is electromagnetic radiation? It's a form of energy and it shows wave-like behavior when it passes through space. Now, the electromagnetic spectrum is actually divided into regions that depend on the frequency or the wavelength and therefore the energy of the radiation. So your electromagnetic spectrum is divided into different regions. Some of you may have used this textbook in your, I don't know, some of the junior classes. It's just called Physics for You. So I've gone and brought up, just want to show you a picture of the of the spectrum. So I can't show the whole thing to you. I probably adjust that. Yeah. So I think you can see the colored line right on top there. That is your electromagnetic spectrum. Okay, so your spectrum, the electromagnetic spectrum, actually goes from short wavelength, which is right there, right up to the long wavelength, which is at the right hand side end. Okay, so short wavelength. Short wavelength means higher frequency, and so the typical rays that you'd find here are the gamma rays. Alright, so where do you find gamma rays? They are found in radioactive substances like uranium, and they're very dangerous. So the next wavelength is for X-rays. X-rays we know come from an X-ray tube. They're also very dangerous. The next one is ultraviolet. So this is the electromagnetic spectrum, and it's divided into, remember how we said it is actually into different spectrum. So that's the ultraviolet spectrum. The ultraviolet spectrum is, a source of it is the sun. One of the sources is the sun, and we use sunscreen because we want to protect ourselves from the UV rays of the sun. So that's where it is. Then you have the visible spectrum. So this is the only spectrum of electromagnetic radiation, of the electromagnetic spectrum, that is visible to the human eye. So that's only that bit, which is 5 × 10⁻⁻7 meters. Alright, the sources are here: hot objects, sun, fluorescent substances, lasers, and LEDs. And then after the visible spectrum, you have the infrared, and after infrared is all your radio waves. Alright, and in that you've got your microwave, the TV and mobile frequencies, radio, and medium wave radio. Alright, so together this is the electromagnetic spectrum for you. And energy will, the matter, so we said spectroscopy is a study of how light or electromagnetic radiation interacts with matter, right? So different components of matter will react with different spectra. So some of them will interact with infrared and some with ultraviolet. So we'll actually look at how this helps us with our study of spectroscopy. Alright, so that was just some background information on electromagnetic radiation. You don't have to copy any of this stuff. This is probably just good to know stuff. Alright, now coming back to what we need for our assessment. There are two spectroscopic techniques that you need to become familiar with, and they are used to identify molecular substances. So the whole idea of going into the spectroscopy is you want to identify what are the components of a substance. So they are used to identify molecular substances, and the two techniques that we need to learn this year, one is infrared, which is IR spectroscopy, and the second one is NMR, which is nuclear magnetic resonance spectroscopy. So those two we need to study. It's probably a good idea to pause the video and just copy this into your books now. Two spectroscopic techniques that are used to identify molecular substances, one IR and two NMR, which is nuclear magnetic resonance spectroscopy. Okay, so you pause the video. When you copy this, you can move on to the next one. So there's a third technique that we need to learn this year, and it's called mass spectrometry. What mass spectrometry does is it doesn't involve electromagnetic radiation, but it actually involves ionizing a molecule and splitting it into its fragments. So you get fragment ions which have a particular mass, and then using those fragments we can piece the molecule together. So one, we can find the molar mass of that actual substance, and 2, we can find out the structure, how it is put together. So that's the third technique that we'll be using. So for this assessment, there are 3 techniques we'll be studying. One is IR, second is NMR, and third is mass spectrometry. Alright, so mass spectrometry is slightly different. It doesn't involve electromagnetic radiation. It involves ionizing a molecule and then splitting it into fragments. So if you haven't copied, pause and copy these 3 as the techniques that we need to study this term. So I'm going to go and give you some details on the first method, which is infrared spectroscopy. So what is infrared spectroscopy? It involves interaction So it involves the interaction between a molecule and radiation from the IR region of the electromagnetic spectrum. So remember that I showed you the diagram of the electromagnetic spectrum earlier. I'm just trying to find that picture again so I can show it to you, and so there we go. That was the spectrum that I had shown you, and so IR spectroscopy actually deals with the interaction between a molecule and radiation that comes from the IR, which is here, that wavelength. All right. So look at the definition again. It involves interaction between a molecule and radiation from the IR region of the electromagnetic spectrum. You can pause the video and copy that down as a definition for infrared spectroscopy. Alright, so remember this term, this assessment requires you to know 3 different techniques. The first one is infrared, the second one is NMR, and the third one is mass spectrometry. So I'm going to start talking about each of these individual techniques. The first one is infrared spectroscopy, and this is a definition for what infrared spectroscopy is. Alright, so pause the video, copy that definition, and when you're done, we can actually just look at an example of a molecule. Alright, so we've got a molecule here, you've got an atom and you've got another atom, and we normally have this plastic pipe or tube here. It represents a bond, right? So however, that's a model, and the bond is not a firm, rigid plastic thing like this. In fact, in reality, bonds are more like spring. The bonds can actually be stretched, they can be compressed, they can be bent, and so bonds are more like a spring. Now, there is different types of bond vibration. So a covalent bond, there's different types of bond vibration in them. There's bending. Okay, so let's take a 3-atomed molecule, like let's say that's carbon dioxide. So carbon, oxygen, oxygen on either end. Okay, so this molecule has covalent bonds. They can be stretching and they can be bending as well. Okay, so there is stretching of bonds and then there is bending of the bond. Now, each of these, this bending and stretching, each movement is a vibration. So the stretching is a vibration, the bending is a vibration, and each one corresponds to a particular frequency of energy. Okay, so it corresponds to a particular frequency of energy. So that's why we're getting into this. So in any molecule, when there are covalent bonds, these bonds can be stretched and they can be bent. Each of these movements is a vibration that corresponds to a particular frequency of energy. I think you should copy that too. Alright, and then what it says is that the amount of energy involved in these vibrations is equal to the energy in the infrared range of the electromagnetic spectrum. So covalent bonds, there is bending, and then there is bending, and then there is stretching, and there is a certain amount of energy involved in these vibrations that is equal to those in the infrared range of the electromagnetic spectrum. So you can pause the video and copy this bit down as well. So we'll now look at how we can interpret an IR spectrum. And that's really where the assessment comes in. So, previously it was all just an introduction. So you can now title on your page saying interpreting an IR spectrum. So how you get an IR spectrum is you pass IR radiation through an organic substance. So let's say I've got a beaker and it is filled with some organic compound. Okay, so you pass infrared radiation through this organic compound, and different components of this compound will either absorb or they will transmit. Alright, so we're going to then plot. So what we get is a spectrum at the end of that, and you can interpret it like this. There's a x-axis and a y-axis. This axis is transmittance, which means how much of it actually goes through without being absorbed. Transmittance, and it is in percentage. And this axis here is wavelength. Sorry, wave number, which is the unit for that is per centimeter. Okay, so transmittance on one axis, wave number on the other. The unit for one is percentage and the unit for the other is per centimeter. So transmittance means how much of this IR rays actually just pass through without being absorbed. So it can either be 100%, usually not 100%, like 95% transmitted, like nothing was absorbed, or sometimes you can have absorption. So let's look at what that means. So if you want to copy that down into your book, interpreting an IR spectrum is you basically just taking IR radiation, passing it through an organic compound, and then plotting the transmittance at different wave numbers. Okay, so you can pause the video and just copy the spectrum down. So that is an illustration of an IR spectrum. Okay, so shall show you an example from your workbooks. Okay, so here's an example of an IR spectrum. Have a look at what I've just taught you. Is that you have the transmittance on the y-axis, which is in percentage, and then you have wave number, which is per centimeter as the unit. And then you see that there are all these peaks or troughs, as we call them. Okay, so they're all corresponding to different wave numbers. Okay, so the first thing is that the IR spectrum can actually be split into two regions. This part of the IR spectrum, which between 1,500 to 4,000 per centimeter, that is called as the functional group region. So any functional groups that are in the organic compound that you are analyzing, they will be, they'll show up in this region. Whereas lower down here to my right, you have what is called as a fingerprint region, which is anything less than 1,500. Okay, so in the graph that we drew earlier, I'm going to put in some more details. So I would say, I'm actually going to draw it out again because I don't have much space to write anything. Okay, so my y-axis is transmittance, which just means how much of those infrared rays have passed through, and that is always in percentage. And on this axis is my wave number, and the unit for that is per centimeter, because it's 1 over lambda, so which is per, then you bring it up, it's per centimeter. Okay, so it goes, the infrared region is from 4,000 down here to 500. Between 4,000 and 1,500, so that's 500, that is 1,000, that is 1,500, that would be 2,000, and that would be 3,000. So this region here is called as the functional group region. Alright, so between 4,000 and 1,000, so sorry, 1,500 to 4,000 is the functional group region. That means any spectrum that you get here will relate to the functional group. You know what functional groups are. It could either be representing carboxylic acid or an amide or an amine, etc. So those are your functional groups. Lower down here, which is less than 1,500, this part here is called the fingerprint region. And I'll tell you in a minute what fingerprint region is. Okay, so in the fingerprint region, which is less than 1,500 or 1,500, most compounds have quite complex IR spectrum. So you'll actually see a lot of peaks and troughs in that area. Okay, so below in the fingerprint region, it's quite complex, and that is due to bending vibrations. So remember, we said there's two types of vibrations. They can bend or stretch, and that's usually due to the bending. An unknown compound can be identified if this fingerprint region of the spectrum is the same as that of a known compound. So basically, just like our fingerprints, all right, so if you've seen your fingerprint, you can use your own thumb and see what the fingerprint is unique for each person, right? It is like your signature. So exactly the same way, a compound, that part, the fingerprint region, will be unique to it. So basically that's what they're saying. So if you have some unknown compound, so I have a beaker of some unknown organic compound, I don't know what it is, it can be identified if this fingerprint region of the spectrum is the same as that of a known compound. So we do some tests like we've done, we know how to identify for, let's say it's an alcohol. So I suspect it's an alcohol. I can compare that fingerprint region to this known spectrum of a similar alcohol. That's what they mean. But most of the information regarding the structure of the molecule is gained from the functional group region. So that is the part that we want to focus on. The functional groups that are present in the molecule can be identified because this is a stretching. This is where the stretching frequency comes in. The C double bond O, the carbonyl group, the CH, there's a stretching there, C double bond C is a stretching, and CO and OH bonds, they absorb at different frequencies. The exact frequency depending on the neighboring atoms to which the group is attached. So what I'm going to do is just on my graph here, on my spectrum here, I'm going to say that the functional groups can be identified because the stretching frequency of those different bonds, they absorb at different frequencies. So I'm just going to copy that paragraph onto the graph to say to actually highlight the importance of the functional group. So you can copy with me as I'm writing. Right, so functional groups present in the molecule can be identified because the stretching frequency of the C double bond O, CH, C double bond C, CO and OH bonds absorb at different frequencies. The exact frequency depending on the neighboring atoms to which the group is attached. So if we so you can actually pause and copy this down into your books. Alright, so going back to your ESA study guide, your textbook, and if you don't have it, it's fine. You can just follow with me. There are certain names that you now need to get familiar with. Each trough or the upside down peak is actually called as a band or a peak. We call them peaks. Typically we think peak would be something that goes up, but I don't know, chemists will just call these peaks as well. So we say that there is a peak at that would be around 3,500 there, between 3,200 and 3,500 actually stretches over a range. So let's read what the sentence says. A spectrum of any molecule with an OH group. So if that molecule has an hydroxyl group, which is part of its structure, that group will usually have a very broad or wide and characteristics peak at about 3200 to 35. Now notice how they always start with the smaller wave number and go to the larger wave number. What is it? That's exactly how you need to write it in the exam as well. So some key words here is that we call them as a wide or a broad peak. Okay, and it is between 3200 to 3500 per centimeter, and that indicates that organic molecule has an OH group in it. And why is that? It is due to the presence of intermolecular hydrogen bonding that pulls some electron density away from the OH bond, lowering the frequency of the stretch. So they've given you a reason as well. Okay, so again, so basically if it's an OH group, it will be there will be a wide or a broad peak, at 3200 to 3500 per centimeter, and is due to the presence of intermolecular hydrogen bonding that exists between groups that have OH groups in their structure, and that actually what it does is it pulls electron density away from the OH bond, lowering the frequency of the stretch. On the other hand, so that is typical of an alcohol group. Okay. On the other hand, look at this spectrum here. They tell us that this is a spectrum of an amine. Now, if you compare these two spectrums, you can see straight away. So what is similar is that it's always a plot between transmittance, which is on the y-axis, which is in the unit is percentage, with wave number, which is on the y-axis, and the unit is centimeter to the power of -1. That's what is similar. And the x-axis is always from 4,000 to 500. Or less of 4,000 to 500. And your percentage is always out of 100, right? Okay. Now, looking at the amine and the alcohol, the biggest difference is that you do not have that broad peak between 3200 and 3500. You don't have that. It's absent here. So if I looked at the spectrum, I would know straight away. So this is on page 19 if you want to follow with me. If I looked at this spectrum, I would know straight away that this is not an alcohol because it does not have that characteristic broad peak that I would expect. But there's something else instead. Alright? So there is another stretch that we can look up. And it's the stretching of that NH bond is actually in the same region as the OH bond. But the absorption is sharper and it's not so strong. And the reason for that is, so they're actually comparing the OH group with the, which is found in an alcohol, with that of the NH group, which is found in an amine or an amide. So they're saying that the absorption happens in the same region, but it's not as strong. Why is that? Because NH bond is less polar than the OH bond due to the lower electronegativity of nitrogen when you compare with oxygen. Alright, so you will have some activity there, but it's not as strong as an OH group. So I think with that, what I'm going to do is I'm going to actually stop at this point, and I would just let you go through the ESA study guides are in the front of the classroom, so you can go through some of the notes here, and I will also print some material out so you can start reading through them. So for now, I just want you to get a brief introduction to what spectroscopy is, and I'll then continue with this on Wednesday. So you can pause, you can stop the video now, but it doesn't mean you can just do anything you like. Yeah, I've still got some materials for you to read. The other thing is that those of you who haven't done the test, so there were some who were away on Monday, I would need you to come in at lunchtime on Wednesday